Hey everybody, it's Ripley back again. Hope you're having a good day. Excuse me. Today we are going to talk about series. Now, if you recall, a sequence was just a box with a bunch of ordered elements in it, right? And that sucker went all the way up to infinity. And if I took the limit as in goes to infinity of a sub n, right? This a sub n, which came from f of n, of course. If this equaled an L, then it diverged. Otherwise, it converged else, right? Now, what a sequence is it's the sum of those things. So a sequence, I take a sub 1 plus a sub 2 plus a sub 3 plus dot, dot, dot. Now, I can have a finite sequence, which, of course, will converge as long as all of the values are defined, or I can have an infinite sequence. And infinite sequences are far more interesting. When I write it like this, it's kind of a more interesting way to write it. You'll often see this written as the sum as n goes from 1 to infinity of a sub n, or if you're slightly more lazy, which I can be from time to time, you see it written like that. Excuse me. Okay, so before we get too far ahead of ourselves, let's give ourselves a little bit of vocabulary to work with, and then we'll start talking about some specific series. All right, so these are sequences, these are series. Add them up. And we'll talk about, you may be going, Ripley, how can an infinite set of points converge? Why are those interesting? Why do we have why are we even having this discussion? Well, we'll talk about some interesting series that you actually have explored back in your pre-calculus times. Okay, so let's talk about partial sums. A partial sum is written like this. What you'll often see is like S sub 1 equals A sub 1, S sub 2 equals A sub 1 plus A sub 2, S sub 3 equals A1 plus A2 plus A3, and then dot, 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 S sub n is equal to A1 plus A2 plus A3 plus dot, 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 plus A sub n, right? True? All right. Another thing that's kind of interesting to look at is if we think about if excuse me, if a series is going to converge, an infinite series, that means that it goes to a number. That means that the limit as n goes to infinity of S sub n is going to equal some number. Geez Louise. All right. Anyway, so we're familiar with convergence and divergence at this point. Hopefully that's not too scary for you. Let's see. Another way to think about these is, can you see that S sub n could be written as S sub n minus 1 plus A sub n? Let me show you. S sub 8 could be written as, that's too many. I'm not writing that many darn terms. Let's go S sub 6. I'm feeling a little lazy today. This is going to be A sub 1 plus A sub 2 plus A sub 3 plus dot, dot, dot plus A sub 5 plus A sub 6. So this guy right here we know is S sub 5. So S sub 6 could be written as S sub 5 plus A sub 6. So if we generalize that term, whoop, we get this guy right here, which is an absolutely beautiful thing. Okay, so excuse me, if S, this S right here that we're talking about, if S is equal to a number, this implies that the infinite series converges. If not, else it diverges. So but in terms of convergence and divergence, it's still very consistent with what we've spoken about before when we were talking about convergence and divergence in other contexts with our integrals, with our sequences, and now we've moved on to our series. Okay, so you've seen these in pre-calculus before. This is nothing new to you, hopefully. Now we're going to talk about a couple of specific series, and then we'll be on with it. Okay. All right. Let's talk about geometric series. Geometric series. And again, you saw these in pre-calculus. A geometric series is a series of the form. They're typically written like this. You'll see them as AR to the n, where n goes from 0 to infinity, or the sum as n goes from 1 to infinity of AR to the n minus 1. I think I just said when 0 goes from 0 to infinity. You know me, I'm crazy. Now, let's list terms. The biggest thing with series is when you cannot get your brain around what you're looking at, list the first 3 terms. It'll make your life better. Okay? So what we got is, what's our first term? If I plug in n equals 0, r to the 0 is 0, or excuse me, is 1. A times 1 is A. Likewise, when I plug in n equals 1, I get 1 minus 1, which is 0, r to 0 is 1, times A, etc. Excuse me. I will typically use this notation, but truthfully, you can start n wherever you want, which I'll show why here in just a sec. The next term would be A times r to the first, which would be AR. Again, if I put in 2, I get AR to the first plus AR squared plus AR cubed plus ... And it goes on forever. Okay? All right. Now, I am going to show when a geometric series converges and when it diverges. Okay? And I think that you'll find that it's kind of fun. All right. Watch how this works. We know that a partial sum, by this definition, S sub n is equal to A sub 1 plus A sub 2 plus A sub 3 plus ... plus A sub n. But when we're talking about a geometric series, we know that S sub n is equal to A, right, first term, plus AR. That R is called, I don't think I mentioned this, but this is called the common ratio, right? And I'm moving quickly because, again, you've seen these, but I don't want to be confusing. Remember how geometric series work, right? I just multiply the previous term by the common ratio to get the next term. So I get A plus A times R plus AR squared plus AR cubed plus ... plus AR to the n, right? Keep it simple. That is, if it starts at n equals 0. Okay? Now, I'm going to multiply by r. So I get r s sub n, and what I get is AR, A times r, plus AR squared, plus where am I? AR cubed, geez Louise, plus AR to the fourth, plus ... It's the end of the week, so I'm a little punchy. And this is plus AR to the n plus 1. Right? Now, I'm going to do something a little funky. I'm going to subtract these two quantities. So I'm going to get S sub n minus R times S sub n is equal to, and look at what happens. When I subtract this guy from this, when I subtract these terms from this, well, you got to remember, I probably should have installed just a little teeny tiny, this is going to be plus A sub R to the n plus A sub R, A times R to the n, plus A times R to the n plus 1. That's really hard to wrap your brain around. All right, so when I subtract, cancel, cancel, cancel. This is going to cancel with some term here. This will cancel with some term here. And I subtract, I'm going to get A minus AR to the n plus 1. I'm going to factor out an S sub n, and I get 1 minus R is equal to A times 1 minus R to the n plus 1, right? When I divide through, I get S sub n is equal to A times 1 minus R to the n plus 1 over, over 1 minus R. Now let's think for just a second. If this was the formula for when geometric series were finite. By the way, this is a little bit confusing because had I started this thing at n plus 1, had I started it at 1 instead of 0 is what I mean, then this guy would have just been up to R. I would have had all of the exact same terms. Everything would have worked out the same. In your pre-calc text, you probably saw it written like this. S is equal to A times 1 minus R to the n over 1 minus R. That's important because for this case, this is when n goes from 1 to infinity of AR to the n. This guy here is when I've got the sum of AR to the n, where n goes from 0 to infinity. All right, now I'm going to kick over, I'm going to rewrite that term just so we can see. I know that S sub n is equal to A times 1 minus R to the n plus 1, again, starting at n equals 0 instead, divided by 1 minus R. Okay? Excuse me. Now, remember, if it's finite, it's going to converge as long as all of my terms, as long as all of my, well, my A has got to be defined, right? As does my R. So this thing is always going to converge. So convergence or divergence of a finite series it's vacuous. We don't need to worry about it. We know it's going to converge if it's finite. However, if it's infinite, remember, if I take the limit as n goes to infinity of s sub n, I get s, which is equal to the limit as n goes to infinity of a times 1 minus r to the n plus 1 over 1 minus r. Now, if you recall from our sequences, remember that the limit as n goes to infinity of r to the n plus 1, it could be r to the n, it doesn't matter, it's the same thing. This converges for absolute r, for absolute r less than 1, absolute r less than 1, right? Because this limit will equal 0. This implies that the limit as n goes to infinity of r to the n plus 1 is going to equal 0. Else, it diverges. So long as absolute r is less than 1, in other words, r lives between -1 and 1, we're in great shape. And what does this thing turn into? If this turns into 0, this term right here turns into 0, that implies that s is equal to a over 1 minus r. Again, a pre-calculus topic, but I wanted you to see the proof of it. Now, this is really, really important. And the reason this is so important is we've dealt with infinite series before. Let's say that I do the series of 1/2 to the n, right? And this is, if I start at 0, so when I write it like this, from 0 to infinity, I know this is 1 plus 1/2 plus 1/4 plus 1/8 plus ... Now, the trick that you're always going to do every single time is you're going to identify a, which in this case is 1, and you're going to identify r, which in this case is 1/2. Remember, if this is bigger than 1, if r is greater than 1, you're done, diverge, thank you for playing, I'm out of here. But since r is less than 1, now what do? Well, I just plug it in. S is equal to a, which is 1, always the first term, irrespective of what the first term is. A over 1 minus 1/2, which is r, which is 1 over 1/2, which is 2, which probably most of you knew, okay? Now, for example, let me get crazy. Let me get all kinds of nuts on you. What if I were to throw this at you? Let's say that we did n equals 0 to infinity of x over 2 to the n. Wait, Ripley, you're introducing an x? Where's that x come from? Don't panic. Remember, if you can't get your brain wrapped around something, write it up. Okay, so here we go. First term, 1, anything to 0 except 0, of course, plus x halves, this is getting scary, plus x squared, 4, wait a sec, plus, this isn't bad, over x cubed to the 8th, plus ... Hey, wait a sec. Okay, a is 1, that's my first term. R is, what am I doing? X over 2. So s is equal to 1 over 1 minus x halves. Common denominator, this turns into 1 over 2 minus x over 2, which is 2 over 2. Whoa, that's crazy. Now we got to be careful. Remember, this is only true if the absolute value of x halves, which is my r, is less than 1, right? By the definition of convergent infinite series. This is only true if and only if absolute x is less than 2, right, if I multiply through, and that tells me that for x between -2 and 2, this series, this is going to blow your mind, and we're going to get into it later in terms of sort of the gravity of this series turns into that function as long as x is between -2 and 2. Mind blown. We will get into writing functions as power series, as series is down the road, but that's pretty cool. Okay? All right, enough said. Now, what if I were to do this to you? What if I were to do 2/5 to the n, and I let n equal 3, and let it go to infinity? All right? Okay, Ripley, what does that mean? Well, don't panic. Do what you're supposed to do. List your first few terms. This is going to be 2 cubed over 5 cubed. That's my first term. Plus, now I got to multiply through by that again, right? I get 2 to the 4th over 5 to the 4th. Plus 2 to the 5th over 5 to the 5th. Plus 2 to the 6th over 5 to the 6 plus dot, dot, dot. Now, you see that to get from one term to the next, my common ratio is 2/5. Now, the problem is, and what students love to do, is they love to assume that the first term always has to be either 0 or 1 or 2/5 in this case. Stop. That's not true. I know that A, the very first term, is 8 125ths. I know that R is 2/5. I always just grab the first term. I don't think. If you start thinking, all hell's going to break loose. I know that this thing has to converge because absolute R is less than 1. So I know that S is equal to 8 125ths divided by 1 minus 2/5, which is 8 over 125 divided by, excuse me, 3/5, right? So I multiply, hopefully you can see that this becomes what, 8 75ths? Let's check, make sure I'm not lying. 5's cancel, that becomes a 25. Flip the 3, last time I checked, 3 times 25 is 75. Who knew? This thing converges to 8 75ths. That's crazy. Okay, we've seen these before. Let's talk about our first test. Our first test is this. Let's say that I have a series. I wanted to get you guys on track with the series that you'd seen before, get you comfortable. Now let's get a little crazy. Let's say that I go from n equals 1 to infinity. I only started at 0 when I'm dealing, excuse me, I only started at 0 when I'm dealing with geometric series, unless I'm forced to start at 0 with another series, like if it's a problem on an exam or in the textbook. Okay, excuse me. Do we agree? If the limit as n goes to infinity of a sub n equals any number, we know that a sub n, we know that the sequence, this implies the sequence, the box, converges. We know that. Now, what's to be said if a sub n equals a limit about the series? Well, what will happen? You'll have an a sub 1, this will equal a sub 1 plus a sub 2 plus a sub 3, and then somewhere along the line, we're going to get our limit, aren't we? It's going to hit our limit. So we're going to get numbers really close to our limit, so arbitrarily close to our limit that we're not going to be able to tell the difference. Now, hopefully you can see that irrespective of what happens for these terms that are bebopping around, we have no idea what they're doing, and then all of a sudden, the series, remember, the sequence, a sub n, comes from f of n. But all of a sudden, the sequence values in the series calm down and everything heads for this L value. Think of it like a horizontal asymptote. Well, if L is not equal to 0, this implies that there's absolutely no way for the sequence to converge. This thing has to diverge. It has to diverge, doesn't it? Because I'm adding, even if L is 0.00000001, I'm adding up an infinite number of those little tiny 0.000001s, and infinity is patient. It takes its time. It doesn't really care how small the number is because it can just keep adding up until it gets out of hand. Okay? So, what does that give us? It gives us our first divergence theorem. So this is a divergence test. Divergence test. All right, the divergence test says this. If the limit as n goes to infinity of a sub n, notice sequence, you got to be real aware of the difference between what you're talking about with in terms of a sequence or a series. If this is not equal to 0, this implies that a sub n diverges. Guaranteed. Done. Thank you for playing. So your first thought with any sequence, like with any series, like for example, if I let n go from 1 to infinity of n over n plus 4, right? We know that the limit as n goes to infinity of n over n plus 4 equals 1, which implies that n, the sequence, n over n plus 4, is convergent. However, because the sequence goes to a value other than 0, since the limit as n goes to infinity of n over n plus 4 does not equal 0. That means out at infinity, what we're basically going to be doing is adding a bunch of 1's together. How many 1's? An infinite number of them. That implies that the series n over n plus 4 diverges. And we're done. So you can have a completely convergent sequence and a divergent series. Okay? Now, here's my question. If it does go to 0, what's up if the limit as n goes to infinity of a sub n equals 0? What happens? Does that guarantee that it converges? We know that if it doesn't equal 0, then it's going to diverge, which means that if, I guess the contrapositive of this is if the sum of a sub n converges, then this implies that the limit as n goes to infinity of a sub n must equal 0, right? Remember from contraposition, from your logic, not this, which is equivalent to saying it converges, implies not this, which implies that it has to equal 0. All right, let's talk about the good old harmonic. 1 over n, as n goes from 1 to infinity. Okay, this is called the harmonic. All right, now something special happens with this. It's the harmonic series. Okay, now again, you know what this thing looks like. It's 1 plus a half plus a third plus a fourth plus dot, dot, dot. Now I want to know clearly the limit as n goes to infinity of 1 over n equals 0, which implies that 1 over n converges to 0. But I want to know if the series converges. All right, let's do this. You ready? This is kind of an interesting proof. I like this. The first two terms are 1 plus 1/2. No doubt about it, right? All right, so this guy right here is s sub 2. All right, now what I'm going to do is I'm going to add on the next two terms. So this is plus 1/3 plus 1/4. So what I get is s sub 4. Now, if you think about this, oh, maybe I should do this. I'm gonna bear with me for a second. Let's kick over here. I'm gonna need more room. So 1 over n, I know that s sub 2 is 1. This is as n goes from 1 to infinity. Sorry, being lazy. In a hurry. I apologize. S sub 4 is going to be equal to 1 plus 1/2 plus 1/3 plus 1/4. Right? Now, if you think about this, I know that this is greater than 1 plus 1/2 plus, now this is going to be a little bit weird, but bear with me, plus 1/4 plus 1/4 because a third is greater than a fourth. Everybody agrees with this. And I know that this is equal to 1 plus 2 over 2, right, which is equal to 2. Now I'm going to do s sub 8. Now you're probably noticing that these are powers of 8s. So this becomes 1 plus 1/2 plus 1/3 plus, I promise I'll only do this one more, or this is the last time I'll do it, plus 1/5 plus 1/6 plus 1/7 plus 1/8. That's what this guy is equal to. All right, now, excuse me, I know that this is equal to, or excuse me, that this is greater than, no doubt about it, I know that this is greater than 1 plus 1/2 plus 1/4 plus 1/4, which is this guy, plus what? 1/8 plus 1/8 4 times, plus 1/8 plus 1/8, because a fifth, a sixth, and a seventh are all greater than 1/8. You could probably see what would happen. Now, let's see what happens here. This becomes, I know that this goes to 2 and this goes to 2.5. So this becomes 2.5, right? Which is really, I guess an easier way to write this is 1 plus 3 over 2. Now, you may be going, wait a second, Ripley, what are you doing? Well, notice what I did here. This is 1 plus 1 over 2. This is 1 plus 2 over 2. This is 1 plus 3 over 2. Now, I'm not going to do the whole thing here, but you probably can see what happens here. I would have 16 terms. I know that the 16 terms, blah, 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 I'm going to have this. I'm going to cheat just a little bit. And I'm going to stick it right here. And then I'm going to have, let's see, what do I have? I'm going to have 1/9 plus 1/10 plus 1/11 plus 1/12 plus 1/13 plus 1/14 plus 1/15 plus 1/16, which I know is going to be greater than, now I'm going to go 1 plus 3/2 plus, now I'm going to add up 1, 2, 3, 4, 5, 6, 7, 8 numbers that are going to be greater than 1/16. So this is going to be, this is greater than, I got 1/16 plus 1/16, 8 times, plus dot, 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 1/16. This is 8 times, right? Now you may be going, Ripley, what are you doing? Well, this is equal to 1 plus 3/2 plus 1/2, which is equal to 1 plus 4/2. Are you seeing what's happening? I know that the sum is greater than this sequence right here. Doesn't this sequence out at infinity turn into, what's it going to turn into? It's going to turn into 1 plus n over 2. And since the limit as n goes to infinity of 1 plus n over 2 equals infinity, we know that this term right here, whoops, well, close enough, is going to diverge. Now, I know that any of my s sub 2 to the n's, which are going, right, this is my 2, wait, 2 to the n, what am I doing? I know, don't listen to me. I know that these guys come from this series, and I know that that if I go far enough out, you can probably see what I would do next, right? I would go s sub 32, s sub 64, s sub 128, which is where I'm getting my 2 to the n. I know all my partial sums are always going to be greater than this, and like I said before, infinity is patient. So I know if this chunk right here turns into 1 plus n over 2 and it diverges because it goes to infinity, then the thing that is bigger than that by the comparison test must also diverge. Now all this implies that the sum as n goes from 1 to infinity of 1 over n is divergent, even though 1 over n converges. And it converges parenthetically to 0. All right, so what did that just prove? Well, first thing it proved is that the harmonic, you're going to want to memorize that, the harmonic, this guy right here, is a divergent series. That's the first thing it gave us. Okay, that's huge because the harmonic series is going to be an anchor for proving of convergence and divergence down the road. That's first thing. What's the second thing it showed? Well, it showed that you can have a sequence that converges to 0 and a series that diverges as a result. All right? However, we know that if it doesn't converge to 0 by the theorem, by the divergence test, we know if it doesn't converge to the sequence, got to be careful with it because it can mean sequence or series. If the sequence does not converge to 0, we are done. Thank you for playing Divergent. Done. Okay? All right, the only other thing you got to worry about around series is since we're talking about sums, you got to remember all your sum stuff. You've got sum rules, right? You got some rules. Excuse me, you got SUM rules. And things like the sum of the sums, strangely enough, is the sum. This is all pre-calculus stuff. The sum of the sums, right? I know the sum of C times A sub n is equal to C times the sum of A sub n. Pre-calculus stuff. The difference is sum and difference, all right? Don't forget your sum rules. They're helpful, they make your life easier, and they help to simplify what can be really, really complicated at times. All right, that's enough of you guys having to listen to me yap away. Have a fantastic day. I'll see you in class tomorrow, and enjoy. Sorry, a little too much caffeine today at lunch. Bye-bye.